Today I'm going to talk to you about a technique that our group is developing we term isomotive dielectrophoresis. And the purpose of this platform is to conduct analysis of individual particles and a population of particles such that we can identify differences in their dielectric properties between them. So each particle and cell can be composed of different entities that would provide a dielectric signature. So maybe its membrane has some particular properties. Maybe there's a shell on the outside. The cytoplasm has some conductivity and permittivity associated with it. And all of these are relatively unknown, and we measure this signature based on a particular impedance technique. And there's various impedance techniques that are out there. One popular one is electrorotation, where based on the electric field that you apply, and this will have a rotational response based on the electric field, and based on the rotation speed you can obtain a spectra based on the AC frequency that you apply. And this is a popular and robust technique that's been applied, but the disadvantage of this particular technique is that it is a low throughput. And this is where hopefully we can improve upon this, because these dielectric spectroscopy techniques in general are label-free and they're non-destructive. You could potentially do a cell sorting technique downstream. Also, it does not alter cell physiology. I say this, most cases you have to put a low conductivity solution for these cells and particles, but typically it's for a limited amount of time. Now, there are techniques that exist. I mentioned that. Flow cytometry is not a dielectric technique, but this is mentioned here just for comparison. But you have electrorotation, you have electrical impedance spectroscopy, where there is a dynamic technique, meaning you can have a higher throughput, but you only look at a single frequency or a couple of frequencies, whereas a static technique, you hold a particle in place to get that complex spectrum similar to electrorotation. And then here's the technique that we are developing. We are developing an isomotive dielectrophoresis technique where all these electrokinetic techniques are indeed label-free. This is where we meet a need. These flow cytometry techniques are very expensive, they are very sensitive, and then these electrorotation techniques are generally less expensive than flow cytometry. There is some microfabrication involved, but they have a very low throughput. You can say the similar characteristics with respect to dynamic and static electrical impedance spectroscopy systems. For isomotive dielectrophoresis, we hope to improve upon this number, but this is a realistic number where we are right now. We're working on automation to improve this, but we are going to have a negligible or relatively inexpensive fabrication and operation expense compared to these other devices, as well as have as good of sensitivity compared to these other impedance techniques. So what happens is that we apply an external force. This is a dielectrophoretic force. And the curvature and geometry of our system as such that the force is uniform everywhere in our micro device. Why that's important is that all the particles within this microchannel can be analyzed simultaneously because they're all exerted by the same force. So a wider field of view with all these particles being manipulated, and then we track their velocity. We apply a particular AC frequency, we track them, and based on their velocity due to the particular AC frequency that's applied, we can obtain a spectra similar to the rotation spectra of electrorotation. But the fabrication here is much less involved, as well as the throughput is much higher compared to electrorotation. So we're currently developing two platforms. One is electrode-based, where the sidewalls of the channel are electrodes, and there's their particular geometry to do what we want in terms of a dielectrophoretic response. You can also have another geometry in terms of an insulative feature. So these are plastic sidewalls. So in terms of manufacturing, we can look at it from, say, an injection molding type of process on the right, whereas an electrode, more complex microfabrication but more precise technique on the left. We're currently developing both platforms. Here are some preliminary results where we have some plastic particles, both with an electrode-based system as well as an insulative-based system. In videos of this are shown on the next slide. So here we apply a particular AC frequency, we track the velocity of these particles, we can apply various frequencies. These are simple particles, so they will have the same response based no matter what frequency we apply to them. But the more complex particles we have will have a different response, a faster velocity, maybe a velocity in the opposite direction, but effectively we track the velocity of each individual particle, and from that we can obtain the spectra from each individual particle and extract what we need. So we can analyze tens to hundreds to thousands of cells within one setting and then identify small dielectric responses and differences between them. So if you have more questions, please contact me. My email and website address are here, and this work is being currently supported by the National Science Foundation. Thank you for your time.